Today I would like to introduce you to what's called parametric equations. Now, parametric equations are very handy, especially in higher mathematics and in physics. And what parametric equations are is that it introduces a new variable to the equation. So, for example, you're used to seeing equations like this, y equals x squared, and if you graph that, if you graph that on the Cartesian plane, it's going to look something like this. It's going to be a parabola. So you're used to seeing x's and y's in an equation. But what a parametric equation does is that it separates the x and the y, and it introduces a new variable. And it's usually they use the variable t, but they can also use other variables such as theta, or they use theta when representing angles, and they use t when representing time, but you can use other variables as well. But I think these are most common. T and theta are most common. So instead of writing equations like this, what parametric equations does, it writes each of these in relation to t, or time, or to be more general, to the third variable. So say that x of t. So x, instead of just being a variable, it now becomes a function of t, and say that equals just t, and y of t then equals t squared. And you can see that this actually is in fact exactly the same, or at least the graph is going to look exactly the same as that. And let's try to see what this means. Let's draw this on the table. So t over here, x over here, and y over here. When t is 0, x is going to be 0 because x is the same thing as t here. X equals t. And y is t squared, so that's 0 squared, so the y is still going to be 0. When t equals 1, x is going to be 1 as well, because x is t, and y is going to be 1 squared, which is 1. T is 2, x is going to be 2, and y is going to be 2 squared, which is 4. T is 3, x is going to be 3, y is going to be 9. So the t's and the x's are the same in this case, but the y is the square of the t. And let's try and graph this. So these are the points that we're graphing here. We're not actually drawing a separate axis for t. You'll see the role of t in a bit. So the first point would be 0, 0. That'd be right there, 0, 0. And then 1, 1 is right here. And then 2, 4 is right over here. Oops, not there. It's out of the screen, but it's going to be somewhere around here. So if you graph this, if you connect these points, if you connect the points that we just derived, it's going to line up exactly on that red line. And we're only considering the positive part for now, because we're letting t represent time. And it doesn't really make sense to have negative time. So when we have t as the parameter representing time, you usually just deal with the positive portion. So we don't really need to consider the negative t's here. But if you look at just the positive t, it's exactly the same as our previous graph. So what is the advantage of using parametric equations rather than just graphing it like we used to, like that, if it's going to be exactly the same as before? Well, with the introduction of t, we actually know two things about this. So first, we know the direction of the graph. When we just had the red parabola, Let me draw the mini version of that over here. So when we just had the red parabola, we have no idea where this parabola is going. So we don't know if it's going from here towards the right, or if it's going from right towards the left, or it might even be going towards the middle like this from outside, or it might go out from the middle. We don't know the direction of this graph. But with t, when t is 0, the point was right here. And then when t was 1, it was right here. T was 2, it was right here. So we know that the direction is going this way. The graph is heading this way. So as time increases, this parametric equation tells us that this graph is headed in this direction. And another thing that we can know with parametric equation is the location at a certain time. If we just had this parabola here, we had no idea, for example, if the object is modeled with this parabola, we have no idea where the object is when, let's say, t equals 10. Right? We don't know if the object is here or here or here or here. It has no information as to the time, where the object is at a certain time. But if we're looking at the parametric equation, we can find when t equals 10, the object is going to be at 10, 100. Right? So it's going to be somewhere all the way up over there. So as time increases, we can go this way like this. And we can also find the exact location of the object at a certain time when t equals a certain number. So the equation that we looked at in algebra, this equation, is very static. It just gives us what the graph looks like. It just gives us the whole picture. But if you write it in this parametric form, it becomes very dynamic. The graph is moving with the t. As t is increasing, the graph is moving in a certain way. And that's why this parametric equations are very often used in physics. So let's look at an example where we can use that in physics. So let's say that we have a person throwing a ball towards the air. This ball is going to go up, and then eventually it's going to hit some peak, and then it's going to come back down. So as time increases, the ball is going to go this way and then go down this way. So it's moving in this direction. So if you want to know just this overall projectile motion of the ball, then you can just use a normal equation without the parameters. But if you introduce the parameters, we can know where this ball is going to be at a certain time. And if you want to know at what time the ball is going to fall back to the floor, then you can use this the parametric equations to find that. So the throw of the ball can be modeled with these parametric equations. So x of t and y of t. And you might have thought back about vectors, because when we're considering vectors, we treat the x direction movement and the y direction movement separately. So this is kind of similar to vectors. We're treating each of these movements separately, and sometimes it's easier to model these separately rather than trying to model them in one equation. So the x movement of this ball, let's say that the ball was thrown at 10 meters per second, and it was thrown at a, oops, not 16, a 60 degree angle towards the sky. So the x movement of this can be modeled by 10 times cosine of 60, cosine of 60 times t. Now if you don't know why or how I got this equation, that's not important. I'm just giving you the equation for now, and I'm hoping to just illustrate some physics questions, or how parametric equations are used in physics equations. So if you're confused about how I derived this formula, don't be too concerned about that right now. Just focus on analyzing the movement of this given these equations. Okay, so the y direction can be modeled by 10 times the sine of 60, 60. There should be a t there, times t, minus 1/2 9.8 times t squared. Okay, this is the gravitational constant. I'm just gonna use 10 here instead of 9.8 to simplify the calculation. And we can make the table again, t, x, and y. And to save time, I've actually done the calculation in advance. When t equals 0, all of these are 0, both x and y are 0. When t equals 0.3, so after 0.3 seconds, x is going to be 1.5, y is going to be 2.15. And the way you find these is you just plug in t, 0.3 for t. And if you do that on the calculator, you get these values for x and y. And if you do that for other t values, these are the values you'll get for x and y. 4.5, 3.74, and then 6 is going to be 3.19. Okay, so you can see that as time increases this way, the x increases consistently, but for the y part, it increases and then it decreases. From here, it decreased. And that makes sense if you look at this projectile motion here. The y is the horizontal, or the vertical motion, and it goes up until it hits this peak, and then it comes down. That's the y motion. Whereas the x motion, it just keeps going to the right. So that is reflected on this table. As time increases, x increases consistently, but y is going to increase, and then it's going to go and it's going to decrease again. And in fact, the next value here is going to be 1.74. Right? So it increases at a faster rate. Even the rate at which it increases and decreases are different. And that is true for any projectile motion. So with this parametric equation, we can know the location of this ball at a certain time. So after 0.6 seconds after the throw, the ball is going to be in this position at 3 and 3.4. So if you were to graph this on the Cartesian plane, at 1, 2, 3, and then 3.4, so that's where the ball is going to be after 0.6 seconds. Okay, so these are some advantages of using parametric equations. You can know the exact location of the object, and it gives a more dynamic illustration of the situation with the introduction of time as the third variable.